In this video, you'll learn about fiber optic cables. We'll start from scratch. We'll first learn the basic parameters and terms involved in the design of fiber optic cables. We will solve a specific example problem, and then at the end of the video, I'll pose you more conceptual questions for you to get a better understanding. Let's get started with the video. First of all, what is a fiber optic cable? Okay, fiber optic cable is a channel for light propagation. It's a light trap. It's designed such that the moment light enters inside the channel, which is known as the core of the fiber optic cable, it should be trapped inside the core. The layer that surrounds the fiber optic cable is known as cladding. First question, how does the fiber optic cable ensures that light is trapped within the core of the cable? The answer boils down to what is known as total internal reflection. Let's look at what is total internal reflection. When a propagating light wave hits the interface between the cladding and the core, three things are possible. The light wave can get refracted through the cladding. That's possible. The light wave can travel at the interface between the core and the cladding, which will happen at what is known as the critical angle. Or if the angle is much less than the critical angle, it can get total internally reflected. The three cases are possible. Okay, and when will such a total internal reflection occur? That will occur when the refractive index of the core is higher than the refractive index of the cladding. That is, the core is a much denser medium compared to the cladding. In that case, total internal reflection is possible. First question, what is the critical angle at which a propagating light wave will pass through the interface of the core and cladding? How do we get the answer? Pause and think about it. Answer is straightforward. We need to use Snell's law. Snell's law says n1 times sine of the angle at which a light ray hits the interface should be n2 times the angle at which the light ray gets refracted at the interface. Okay? But when the light ray propagates through the interface, what is theta 2? Theta 2 is 90 degrees from the normal. So theta 2 is 90. So this thing becomes sine 90 is 1. So this is the condition for the critical angle theta c. Fine. Now, we know if light hits at an angle that's critical angle or lesser than that, okay, it will get total internally reflected. So what is the angle at which light should enter a fiber optic cable? So what is the angle at which light ray should enter such that there is total internal reflection? Okay, so that light hits this interface at theta c. Let's call that angle theta a, which is theta acceptance angle for a fiber optic cable. This is theta a, and this is the angle at which things get refracted. This is theta r. What is the relationship between theta a and theta r? That is straightforward, again Snell's law, right? Let's call the refractive index of this medium, which is usually air, to be n. So the second Snell's law is n times angle at which light hits the interface, sine of theta a. That should be equal to interface of this, which is n1 times sine of theta r. So as far as light enters the endoscope within this theta a, it will get totally internally reflected. If it enters at an angle that's different or higher than theta a, it will get reflected through the core. Fiber optic cable will not work. Clear? Now let's go solve an example problem based on this. The distal end of an endoscope is placed at a distance of 1 mm from the gastrointestinal wall. The refractive indices of the fiber core and cladding are 1.5 and 1.45 respectively. The maximum field of view for the endoscope is dash degrees. Okay, so we are talking about an endoscope, essentially, which is a fiber optic cable. We are given refractive indices of the core and the cladding. They ask what is the maximum field of view for this endoscope. They have given some additional information saying that it is 1 mm from the GI wall. At this point, the major question that we need to answer is what is field of view? Okay, pause this video, try to answer the question and then get back to the video. Okay, did you try? Did you figure out what the field of view is? Field of view is very simple. We notice there is an acceptance angle, okay, within which the fiber optic cable will work. In this case, the endoscope will work. If the angle is above that, the fiber optic cable will not work. All this angle will kind of form a cone in 3 dimensions, right? The angle of the cone is known as the field of view. So the field of view is 2 times the acceptance angle. All we need to do to solve the problem is to find out what is theta A in terms of the refractive indices N1 and N2. Then we are done. So let's do that. We already wrote down these 2 relations based on Snell's law. So if we could somehow solve for what theta A is based on these 2 relations in terms of N1 and N2, we can in turn find the field of view. Let's do that. I have written the bottom equation in a slightly enlarged form. First thing, let's try to eliminate theta C from this equation because theta A is related to theta R. We notice from the figure that theta C is just 90 minus theta R. Do you agree? Theta C is 90 minus theta R. What is sine of 90 minus theta R? That is cos of theta R. So this is cos of theta R. Okay, now we have a relation in theta R here. Theta A and theta R are related, but we have a sin theta R there. Somehow can we change this into a sin theta R form? Yes, we can convert a cos into a sin theta R using a simple relation, that is cos square theta plus sin square theta is 1. Let's use that relation and rewrite this as 1 minus sin square theta R. Agree? So this is square root of 1 minus sin square theta R. Now let's plug in for theta R from the first equation we have where theta A is hidden. Okay, that gives us n square sin square theta A by n1 square. Now from here we notice we can cancel n1 and this n1 square. Okay, so this is n1 square minus of this by n1 square, and this gets cancelled. So we don't have a denominator here, don't have a denominator here. Now this implies sin square of theta A is, take the square of this, bring the n2 to this side, and n square sin theta A to this side. Okay, so this is n1 square minus n2 square by n square. So sin of theta is square root of this term. Now here comes some approximations. We notice outside of the fiber optic cable we have refractive index n, which is usually air, whose refractive index is 1. So refractive index outside of the cable is 1. So this n square term is just 1 square. Okay, so this whole thing becomes square root of n1 square minus n2 square. Now what is the acceptance angle? Acceptance angle is just sine inverse of this term over here. So theta A is sine inverse of this whole square root. And so let's calculate this for 1.5 and n2 is 1.45, and let's find the field of view to be 2 times theta A, which turns out to be 45.17. Okay, very simple problem, right? Okay, so at this stage, notice we learned a lot of things. N1 is the refractive index of the core, N2 is the refractive index of the cladding. Okay, N1 is higher than N2. Then we learned about the critical angle theta C. Then we learned about the acceptance angle. Then we learned about the field of view. There is one more important term in fiber optics known as the numerical aperture. Numerical aperture is just the term over here in the sine inverse. Okay, so this is n1 square minus n2 square, which makes this theta acceptance angle as sine inverse of numerical aperture. That's my short video on fiber optics. I hope you learn the basic principles of fiber optics, how a fiber optic cable is designed, what are the basic design parameters of a fiber optic cable, and how to use those design parameters in a real world example such as an endoscope. With that, if you have any questions or know about more design parameters in a fiber optic cable, let us all know in the comment section. I'll see you with another video. Good luck.